Hi, this module is about this video is about module 10, mathematics in the medieval world. But what I'm going to talk about is Fibonacci. The readings that you've got will tell you more about what's going on in the world at this time. Not a whole lot. The reason we get to talk about Fibonacci is because he was just about the only mathematician of this time. And poor Fibonacci, he kind of has the reputation of being the greatest of the time, but that's because he didn't have any competition. He really was a very good mathematician. So that's important to keep in mind. Don't neglect what he did just because he didn't have a lot of competition and there wasn't a whole lot else going on at the time. This is called the Dark Ages, the Middle Ages. Lots of wars, plagues. It's just not a whole lot of scholarly work is taking place during this period of time. So let's talk about Fibonacci. He's a really interesting character, did some really neat work. Let's look at the PowerPoint. And you probably have already heard of Fibonacci just because you have heard of the sequence that is named after him. So his real name is Leonardo of Pisa, lived from 1170 to 1250 in Italy, Pisa, of course, and that is Pisa of the Leaning Tower of Pisa. He's known as Fibonacci because that is from the Italian words filius Bonacci. So filius means son of Bonacci, his father's name. So that's where the Fibonacci comes from. Leonardo is probably what his friends and his family called him. Pisa is right over in here. Where is it? It's on the coast. Right there. There's Pisa. So it's right on the coast or near the coast. It's not right on the coast, but it's near the coast of Italy, on the western coast in the Tyrrhenian Sea, close to Corsica, which is the island on which Napoleon was born, and also pretty close to Genoa. Milan is a little bit farther up there in the mountains. Rome is farther down here to the south, not very far from Florence, just kind of a hop, skip, and a jump from Florence. Okay, so that's where he was born and where he grew up. He is known as the greatest European mathematician of the Middle Ages. He was born in Pisa, which was a commercial town connected to many other port cities. And that's important because his father was a customs officer who was stationed primarily in Algeria, in Northern Africa. It wasn't Algeria at the time, but in Northern Africa. And he traveled a lot with his father. He grew up with that North African education under the Moors. He traveled extensively with his father throughout this region. And because of that, he came into contact with the merchants and learned the mathematics that they were using. So they were using that numeration system that had been brought over from India, the Hindu-Arabic system. He learned that system, recognized its importance. He was already very gifted in mathematics. So naturally, he just really took to it. The book that he is most famous for, and he did write a few other things, but the book that he is most famous for is called Liber Abaci, or Abaci. Sometimes you see it with two C's. Liber Abaci, he wrote it in Latin. It means the book of the abacus or the book of calculating. He finished it in 1202. And it introduced the Hindu-Arabic numeration system to Europe. Well, remember I said we'd say that in this next module, just like we did with Al-Khwarizmi. Well, Al-Khwarizmi introduced it through his book that was written in Arabic, and he introduced it to that Islamic empire. Fibonacci took it from the Islamic empire, translated into Latin, which introduced it more widely into Europe. It went up into Northern Europe because of the work of Fibonacci. In this book, just like in Al-Khwarizmi's book, he describes how to use the numbers. He's got algorithms for adding, subtracting, multiplying, and dividing. These are very similar to what we do today. So when you look at that book, and by the way, you can get it on Amazon, the Liber Abaci, go through there and look at those algorithms, and you can see similarities between what we do today. The way he lines the numerals up, so that you've got the tens, the ones place, then the tens place, then the hundreds place. And he adds and he borrows and he carries and all of that kind of good stuff. But that's not all that's in it. It's not just about those numbers. He's got a lot of really kind of fun problems to solve. So interesting problems. They're not easy. You know, some of them you really have to spend some time on, and some of what's difficult about them is trying to figure out, what is he trying to tell me? What is it that I'm given? What is he asking for? You know, he's not saying this in the kind of words that I would be familiar with today. So I really have to do some interpretation and some thinking about what this means. But in chapter 12, we've got that problem that produces the Fibonacci number sequence that we know so well. Starts with a 1 and a 1, and then 2, and then 3, and then so on. This is the problem that introduces that sequence. A certain man had one pair of rabbits together in a certain enclosed place, and one wishes to know how many are created from the pair in 1 year, when it is the nature of them in a single month to bear another pair, and in the second month those born to bear also. All right, so here's the deal with the problem. Let's make a table and see what's going on with this. Okay, so this is very similar to what Fibonacci did in the book. You've got a table with the months and the pairs of rabbits. Okay, so in the first month, Fibonacci said you've got one pair of rabbits. Fibonacci said in the second month, they are going to bear another pair. All right, so if they have another pair of rabbits, now we've got two pairs of rabbits, the original pair plus a pair of baby rabbits. Okay, now I'm going to keep going, and I'm going to come back and talk about this starting point in just a minute. So in the third month, you've got these two pairs of rabbits from the previous month, but only one of them is old enough to have a pair of new babies. The ones that were born in the previous month, they aren't mature enough yet. So I've only got one pair of new rabbits in this month. So I've got 3 pairs of rabbits in this third month. All right, in the fourth month, I've got the 3 pairs from the previous month. But if I go back 2 months, those 2 pairs of rabbits are old enough to have new rabbits. Okay, so these two, each pair of these produces a new pair. So that gives me 2 more pairs. So now I've got 5. And then in the 5th month, I've got the 5 from the previous month. Plus, if I go back 2 months, all of the rabbits from that month, the 3 pairs from that month, can each produce a new pair. So that gives me 3 more pairs, and that gives me 8, and so on and so on. So the rule is that for any month, for the nth month, you would add the number before that plus the number before that one. So let's say that the Fibonacci number in the nth month is the Fibonacci number of the previous month plus the month before that. Okay. Now, frequently, instead of seeing it like that, you will see it like this. Let's go to the next month, n plus 1. Well, in that case, f of n plus 1 would be from the previous month, which is f of n, plus the month before that, which is f of n minus 1. This is probably a more standard way of seeing that formula than this one. I'm not real sure why, but both of those work. They both say the exact same thing. To get the next number, you add the 2 previous numbers. Okay, this again is a recursive formula. So to get down to the 12th month, remember he wanted to go to the whole year. I'm going to have to keep going with this to get the 12th month. Oh, I need to know what the 11th month was, but to get the 11th one, I need to know the 10th one, and so on and so on. Okay. Well, do you remember that sequence that was on the previous slide? It started with a 1 and a 1. And the reason for that is that most people say, you know, let's think about this in 0 months. When we started, you went off and you got a pair of baby rabbits. So you've got a pair of baby rabbits. And it's not until the 2nd month after that that they can produce months. So the standard Fibonacci sequence looks like this: 1, 1, 2, 3, 5, 8, and so on, where the next term is produced by adding the 2 terms before it. Okay. In Fibonacci's book, he presents it like this. And in his table, he's got that the numbers start with 1 and 2. But if you follow the problem closely, you start with 1 rabbit. And in that 1st month, it's not old enough to have rabbit. I mean, start with 1 pair. It's not old enough to have pair. It's the next month when you've got a new pair. Okay. Now, if you go Google Fibonacci sequence, let me come back over here. If you go Google Fibonacci sequence, you are going to see that most of the time you will see the sequence 1, 1, 2, 3, 5, 8, dot, dot, dot. Sometimes you'll see 1, 2, 3, 5, 8, dot, dot, dot. Sometimes you will see that it starts with a 0. If it starts with a 0, that is just wrong. No, it doesn't. The Fibonacci sequence, the historical Fibonacci sequence, does not start with a 0. You can certainly have a Fibonacci-like sequence that starts with any 2 numbers you want it to. But using this rule, using this rule, you're going to have to start a sequence with 2 numbers. Pick 2 numbers. Pick 3 and -3. Well, then you can build a sequence that is generated like this one, but it would not be the Fibonacci numbers. Okay. This is a really famous Fibonacci. I mean, this is a really famous number sequence. And in fact, there is a journal today called the Fibonacci Quarterly that is devoted to research articles about these Fibonacci numbers. All right, let me go back to the PowerPoint right here. All right, so this is taken exactly out of his book. This is exactly the way he states the problem. But we see Fibonacci numbers all over the place, and I'm just going to kind of zip right through this. Take your time and look at this, and even I'll show you in just a second. Flowers, when the next time you go buy some flowers or you're at the grocery store and look at some flowers, count the petals, because many flowers, not all of them, but many flowers, the number of petals is a number in the Fibonacci sequence. And I checked that out on my back porch not too long ago. I had a lot of flowers that had 5 petals. I had 1 that had 3, and I had 2, I think, that had 8. So you see that an awful lot. Daisies, same thing. Pineapples, this is so cool. This is absolutely positively true. Go buy yourself a pineapple. And if you haven't paid much attention to it, I mean, you know the little sticky parts on the outside, but they spiral. And you see that on this bottom row. There are actually 3 different types of spirals there. If you start at the top of that pineapple and you mark the first one somehow, take a thumbtack or something, mark it, go all the way through, and then come back up to the top and mark the second one, go all the way through, and then mark the third one, go all the way through. There are only 5 of those if you're going in that clockwise, almost horizontal direction. Take a different spiral, there are 8 of them. All the ones that's almost vertical, there are 13 of them. I guarantee you. That's just amazing. Now, if you do that standing in the grocery store, they may ask you to actually buy the pineapple. but fresh pineapple's awfully good. Thistle swirls, I don't recommend that you try to count these. It's just too darn hard. But 13 going in one direction, 21 going in the other. Pine cones, different pine cones have different numbers of swirls in there. And copy this into your browser. It's got all kinds of information about the Fibonacci number sequence. This is really cool. In a colony of honeybees, there's only one. I mean, you've got male bees and you've got female bees. The queen is the very, very special female bee, and she is the one that lays the eggs. The other female bees are the worker bees, and they don't lay eggs. They just do the work. So the female bees are, the queen is the only one that produces the eggs. Okay. Well, those eggs hatch and they become either females or male bees. If those eggs have not been fertilized, they produce the drone bees, which are the male bees. Male bees come from unfertilized eggs. The female bees come from fertilized eggs. So if you think about it, a female bee will have two parents, a male bee will only have one parent, and for all of them, their female parent is the queen. Okay? So if we try to make a family tree of this male bee, these are the symbols for male and female. So that one at the very bottom is the symbol for male. And at that stage, I've just got one male bee in this generation. I'm going to back up in the family tree. That one male bee comes from an unfertilized egg, so he just has a queen as his mom. So he's got a female mother, no father. So there's one person on that in that generation. But that queen is female, so she comes from two bees. I mean, she comes from an egg that was fertilized. So she has a male and a female parent. The male comes from an unfertilized egg. The female comes from a fertilized egg. Work your way backwards. And at each generation, count the number of bees in that generation. It's the Fibonacci sequence. Isn't that amazing? Wow. Okay, you see it in other places. Another place where you see the Fibonacci sequence is the golden ratio. And I need a piece of paper over here. All right, we're going to take this sequence of terms and make ratios. So let me stop sharing and come over here. Here's the Fibonacci sequence. One, 2, 3, 5, 8, 13, and so on. And I'm going to make a new sequence where I'm going to make fractions where I take consecutive terms in this sequence. And I'm going to take the larger number over the smaller one. So I'm going to start with the second number over the first one, 1 over 1. And then the third one over the second one, 2 over 1. And then 3 over 2, 5 over 3, 8 over 5, 13 over 8, and so on and so on. All right, that's a sequence. Okay. What happens with this sequence? Well, it's kind of hard to tell when we're writing them as fractions. Let's write them as decimals. This is 1, and then 2, 1.5, 1.66 with a dash over it, 1.6, that's 1 3/5. 1.625 is 1 5/8, and so on and so on. What's happening here is that we're at 1 and then 2, come into 1 1/2, come into 1 2/3, 1 3/5, 1 5/8. My fingers are getting closer and closer to each other. This is a convergent sequence. In fact, it's an alternating convergent sequence. My limit's right here, but the terms in the sequence are going too little, too big, closer, 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 closer. They're zeroing in on it, coming in from both sides. That's what alternating means. And that number that's in there in the middle that they're getting closer to is the limit, right? The limit is the number that the terms are approaching. What is that number? All right, well, we're going to figure it out. As we get really far out here, we're getting closer and closer. And we're going to pretend like we're right out there, right on top of it. So if I'm way out there, right on top of it, I've got these two numbers, A and B. And I know the next number is A plus B. And then the next number would be A plus B plus B, and then so on and so on and so on. All right, well, let's look at these two, the two ratios that I get here. I get B over A, and I get A plus B over B. Well, at the limit, these two fractions would be equal to each other. If we could get to that limit, they would be equal to each other. And what I really want to know is, what is that number, which is B of, what is B over A? That's the limit. All right, let's let B over A equal X. That's what I want to solve. All right, let's take this equation, B over A equals, let's separate this fraction on the right-hand side, A over B plus B over B. And let's substitute in X. Let's get an equation in terms of X. I get X equals, if B over A is X, A over B is 1 over X, and B over B is 1. And then if I multiply everything by X, I get X squared equals 1 plus X. And rewrite that in standard form, X squared minus X minus 1 equals 0. And when I solve this equation using the quadratic formula, I'm going to get X equals the opposite of B, so the opposite of -1, plus or minus, but these are all positive numbers, so I'm not going to get anything negative. I only want one solution. So I'm just going to take the positive square root of B squared, which is -1 squared, minus 4 times 1 times -1. All of that over 2 times 1. And now let's simplify. The opposite of -1 is 1 plus the square root of 1 plus 4 over 2. And that's X equals 1 plus the square root of 5 over 2. This is known as the golden ratio. Square root of 5 is between 2 and 3. So this is between 3 and 4. This is between 1.5 and 2. The golden ratio sometimes is represented with the Greek letter phi. Because it is a very well-known ratio. It is the limit of this sequence. It's not a term in the sequence, it's the limit of the sequence. And that's the sequence of ratios of consecutive terms in the Fibonacci sequence. Okay. So if I go back to our screen, there you go. So there's the exact value of the golden ratio. It is exactly 1 plus the square root of 5 over 2. And by the way, you could sometimes you'll see the golden ratio and they took the ratio of the smaller one to the larger one. This is much more common. Phi is considered to be about 1.6. Okay. Some people say they like math because everything is certain. Well, it's not always so. All right, well, where do we see this? Think about your index cards. 3x5 index cards, 5x8 index cards. Look at those numbers up there in that ratio. 5/3, 8/5. The ratio of the sides of an index card is very close to a golden ratio. And when a rectangle has its side lengths in that ratio, it's called a golden rectangle. A piece of paper that you write on, its measurements are pretty close to a golden ratio. There you go. We just did the math. All right, you see the golden ratio an awful lot in the Vesuvio Man. Different ratios of body parts. Mona Lisa's face fits exactly into a golden rectangle. The Parthenon fits into a golden rectangle, and then parts of the golden rectangle, parts of the Parthenon do as well. I think this is the last one. Yeah. Mona Lisa's face fits into a golden rectangle. This Vesuvio Man was originally drawn by Leonardo da Vinci. He was really big on that golden rectangle. St. Jerome, another one of his paintings, fits into a golden rectangle. If you remember the movie, the one with Tom Hanks, the Dan Brown movie, not Angels and Demons, the Da Vinci Code, of course. The Da Vinci Code was named after Da Vinci. And it had all kinds of clues in there about Da Vinci and the Fibonacci numbers and all kinds of neat stuff. You might want to go back and watch it again now that you've seen this part and thought about it a little bit. And really pay attention to the math that's in that movie, or read the book again and pay attention to the math that's in that book. Okay. All right. So there you go. We are up to module 10, and I will post a review sheet for our exam, and you can get started on that. And then we'll move on to the next group of modules. See you soon.